Every enforcement layer in this arc has been answering some version of the same question. Should this specific request be allowed right now? The mesh answered it with mutual TLS and policy. The gateway answered it by validating schemas and rate limiting the caller. Last episode, eBPF answered it by watching what a process actually did at the kernel, underneath whatever it claimed to be doing. 6 episodes, 6 different places in the stack to say yes or no. Here's what none of them actually decide: what yes or no is supposed to mean in the first place. That's a modeling question, not an enforcement question, and it's also where Kestrel Health's authorization story actually began, years before any of the infrastructure from the rest of this arc existed. Strip away the enforcement mechanism, mesh, gateway, network segment, kernel hook, and every access control system on Earth is answering exactly one question: can this subject perform this action on this resource right now? A subject is usually a user, sometimes a service. An action is read, write, delete, approve, whatever the operation is. A resource is the specific thing being acted on. This record, this file, this endpoint. Everything this arc has built is plumbing that carries a request to that question and carries the answer back out to wherever it needs to be enforced. What differs, and what this episode is actually about, is how the answer gets computed. There are 3 major families for that computation, and they trade expressiveness against simplicity in a way that doesn't show up as a problem on launch day. It shows up a couple of years later, when the real-world permission structure has outgrown whatever model you picked, and by then, the fix usually means rebuilding, not patching. Kestrel Health's authorization story is a clean example of exactly that arc, because it happened in the order most organizations go through it: role-based, then attribute-based, then, for the specific problem that actually mattered, relationship-based. Role-based access control is the model almost every system starts with, and for good reason. A role bundles a set of permissions. A nurse role can view vitals and log medication administration. An administrator role can manage user accounts and system configuration. And a user gets access by being assigned to one or more roles. Kestrel's original system, built years before any of this arc's enforcement infrastructure existed, had 3 roles: doctor, nurse, and admin. Doctors could view and edit patient records. Nurses could view records and log vitals. Admins could manage accounts. The strength of this model is real, not just historical inertia. It's simple to build, simple to explain to an auditor, and simple to reason about. To know what a user can do, you look up their role and read the permission list. A compliance review that asks who can access patient records has a one-query answer. For a system with a small, stable set of job functions and permissions that don't vary by context, RBAC is close to the correct answer, not a compromise on the way to something better. The problem was never that RBAC is a bad model. The problem is what happens when the real world's permission needs get more specific than 3 roles can express, which, at Kestrel, took less time than anyone expected. Here's exactly where it broke. A doctor role that lets any doctor view any patient's record is technically accurate to what the role name says, and it's also far more access than almost any single doctor actually needs day to day. A doctor should be able to see the patients on their own care team, the ones they're actually treating, not the entire hospital system's patient population. But doctor as a role has no way to express only their own patients. The role is coarse by construction. It describes a job function, not a relationship to a specific record. 2 ways to try to fix that inside pure RBAC, and both are bad. One is to leave the doctor role as broad as it started, which means every doctor at Kestrel could technically pull up any patient's chart, whether or not they'd ever treated that patient. a violation of least privilege, sitting quietly inside a system nobody flagged as broken because access control was working in the narrow sense that unauthenticated people couldn't get in. The other is to try to carve the role finer. Cardiology day shift attending, cardiology night shift resident, and so on for every department, shift, and seniority combination, which is role explosion. The number of roles grows to match the number of real-world contexts, until you're maintaining hundreds of roles that are really just permissions wearing a costume, and the simplicity RBAC was supposed to provide is gone. Kestrel hit this exact wall, and it's the wall that eventually pushed them toward a different model entirely. Attribute-based access control throws out the fixed role list and computes the decision at request time from attributes of 4 things: the subject making the request, the resource being requested, the action being attempted, and the environment the request is happening in. A policy isn't a static table anymore. It's closer to a function. Given these attributes, return allow or deny. The example that actually matters for Kestrel's case: a doctor can view a patient record if the doctor is assigned to that patient's care team, and it's during their shift. Notice what that expresses that no fixed role ever could. It's not doctors can view records. It's a condition computed from who this specific doctor is, which specific patient's record this is, and when the request is happening. Swap in different attributes, and the same engine expresses completely different policies without touching any role definitions. A nurse can administer medication only for patients on their assigned floor. A billing clerk can view financial records only for patients discharged some minimum number of days ago. An emergency department physician can override normal care team restrictions during a declared mass casualty event. That last one is the kind of contextual, conditional rule that's simply inexpressible in RBAC's static permission table. And it's exactly the expressiveness gap that pushes organizations toward ABAC once role explosion becomes unmanageable. That expressiveness has a real cost, and it isn't computational. Modern policy engines evaluate these functions in microseconds. The cost is auditability. Ask who can view this patient's record under RBAC, and the answer is a role membership list, readable in one query. Ask the same question under ABAC, and the honest answer is, it depends on who's asking, when, and what the patient's current care team assignment happens to be at the moment of the request. There's no static list to hand an auditor. Because the policy is logic, not data, you can trace what a specific request would do. You can't easily enumerate every possible outcome the way you can read a role table top to bottom. This is exactly the terrain Open Policy Agent from episode 15 was built to manage. Centralizing that logic into ReGO policies evaluated by a dedicated policy decision point doesn't remove ABAC's audit complexity. But it does make the complexity visible and testable in one place, instead of scattered as ad hoc conditionals across every microservice that happens to need an authorization check. If your permission model genuinely needs conditional logic, the same doctor getting different access depending on shift, care team assignment, and declared emergency status, the answer isn't to avoid ABAC. It's to centralize it somewhere you can actually test it, which is precisely the argument episode 15 made. Lay the 3 side by side, and the trade-off is a straight line, not 3 unrelated options. Role-based access control, a static table, user to role to permission, simplest to build, simplest to audit, cheapest to reason about, and coarsest because a role can only express a job function, never a specific relationship to a specific record. Attribute-based access control, a function over subject, resource, action, and environment attributes, evaluated at request time. far more expressive than any fixed role table, capable of encoding conditions RBAC structurally cannot, and harder to audit, because the policy is logic rather than a static list you can read top to bottom. Relationship-based access control, which we're about to get into properly, computes the decision by walking a graph of relationships between subjects and resources. Is this user a member of the team that owns the folder that contains this document? Which is the most natural fit for anything that's fundamentally about sharing and nested ownership, and the hardest of the three to get consistency right on at scale. None of the three is strictly better than the others across every dimension. Each is the right answer for a different shape of permission problem, and the mistake, which we'll come back to near the end of this episode, is picking one because it's familiar, rather than because it actually matches the shape of what you're protecting. Relationship-based access control asks a different question entirely. Not what role does this user have, or what attributes match this policy, but what is this user's relationship to this specific resource, traced through however many hops that relationship actually requires. The canonical example is document sharing, because it's the domain where RBAC and ABAC both start to feel awkward. Can this user view this document? Maybe directly. The document was shared with them by name. Maybe not directly at all. The user is a member of the engineering team. The engineering team owns the Q3 planning folder, and this document lives inside that folder. No role mentions Q3 planning. No attribute captures nested folder ownership cleanly. The permission exists purely because of a chain of relationships: user to team to folder to document. This is precisely the shape of Kestrel's actual clinical problem, described differently. This doctor can view this patient's record because this doctor is assigned to this patient's care team isn't a role statement, and it isn't cleanly a static attribute either. It's a relationship, computed by walking a graph, doctor to care team to patient to record. Model authorization as a graph of who's related to what. And questions like that stop being edge cases you bolt onto RBAC with exceptions and become the actual native shape of the query. Google's Zanzibar paper, describing the system that actually authorizes access across most of Google's own consumer products, including Drive, Calendar, and Photos, is the reason this pattern has a name and a body of production experience behind it, rather than staying a nice idea in an access control textbook. The core design is a single global authorization service that stores relationships as simple tuples. This document has this user as a viewer. This folder has this team as an owner. This team has this user as a member. And answers can user X do action Y on object Z by walking the graph those tuples describe, however many hops it takes. The genuinely hard problem Zanzibar had to solve wasn't expressing relationships. Graphs aren't new. It was consistency at global scale. If someone revokes your access to a folder and a fraction of a second later you make a request that gets checked against a server that hasn't yet received that revocation, you've just been granted access you were specifically removed from. A stale read turning into a real security failure, not a cosmetic bug. Zanzibar's answer is a consistency mechanism that lets a check request effectively say, evaluate this against a state at least as current as the last change I know about. So a permission change becomes visible everywhere it matters before it's allowed to matter anywhere, instead of leaking through whichever replica happens to be running a few seconds behind. That guarantee, at the scale Zanzibar actually runs at inside Google, is the specific engineering achievement the paper is known for. Not the graph model itself, which is conceptually simple, but making that graph model both fast and provably consistent. at a scale most authorization systems never have to face. Zanzibar itself isn't something you can download. It's an internal Google system described in a paper, not an open source project. But the ideas in that paper turned out to be exactly what a lot of organizations outside Google needed. And two real open source systems built directly on Zanzibar's model are worth knowing by name. OpenFGA, originally developed at Auth0 and now a cloud-native computing foundation project, implements the same relationship tuple model and the same style of authorization query packaged as something you can run yourself. SpiceDB, built by AuthZ, takes a similar Zanzibar-inspired approach with its own schema language for defining relationships and permissions. Neither is a drop-in port of the paper's exact internal architecture. Both are independent implementations of the ideas, not copies of Google's actual code base, and each makes its own trade-offs on schema design and consistency tuning. What matters architecturally is that ReBAC stopped being a Google-only capability once these existed. If your permission problem looks like Kestrel's, access driven by chains of relationship rather than fixed roles or computable attributes, there's now real, production-tested, open-source tooling built specifically for that shape of problem, instead of forcing it sideways into a role table or a policy engine condition that was never quite designed for it. None of this makes RBAC or ABAC obsolete, and treating ReBAC as the universally superior answer is its own mistake. The honest guidance is closer to matching the model to the shape of the permission problem you actually have. RBAC is right when the permission structure is genuinely simple and stable. A small, well-defined set of job functions where access doesn't depend on context or on a relationship to any specific record. It's still the correct default for a lot of internal tooling and administrative systems, and reaching for something more complex when RBAC actually fits is its own kind of over-engineering. ABAC, run through a policy engine like OPA, is right when the logic is genuinely conditional. Access that depends on time, location, declared emergency status, or any combination of attributes a static role can't encode, but that doesn't fundamentally revolve around chains of relationship between specific records. ReBAC is right when the domain is deeply relational and sharing-heavy by nature. Documents, folders, anything that looks like a social graph, where the permission question is really a graph traversal question in disguise. And critically, these aren't tiers you pick one from and discard the others. Real systems commonly layer all three broad role-based categories for coarse capability classes, a policy engine for conditional logic layered on top, and a relationship graph as the source of truth for anything genuinely about ownership and sharing, with the policy engine calling out to the relationship store as one more attribute in its evaluation rather than the three models competing for the same job. Here's how that layering actually looks inside Kestrel, and it's the point this whole arc has been building toward. The three-role doctor-nurse-admin structure didn't get thrown away. It still answers the coarse question of what category of user this is, and it's still simple and auditable for that purpose. Open Policy Agent, already in place since episode 15, as the centralized decision point for the rest of this arc's enforcement layers, still evaluates the conditional logic, shift timing, declared emergencies, department-level rules. What got added on top is a relationship layer, modeled in ReBAC style, that answers the one question none of the rest of the system could. Is this specific doctor actually on this specific patient's care team? That relationship check becomes one more input, OPA's policy queries at decision time, rather than a separate system bolted on beside it. The three models layered, each doing the part it's actually good at. This closes a loop worth naming explicitly, back to episode 18's discussion of BOLA, broken object-level authorization. BOLA happens when an API confirms a user is authenticated and holds some general permission, but never checks whether that user has any actual relationship to the specific record being requested. Patient record 4471, not patient records in general. Rate limiting and schema validation at the gateway, from episode 18, catch a lot of API abuse, but they can't catch this because BOLA isn't a traffic shape problem. It's a modeling gap. The authorization system was never asked the object-level question in the first place. An authorization model built to express relationships, this doctor, this patient, this care team, is what closes that gap at the design level, before a request ever reaches a gateway to be rate limited. That's the real argument for getting the model right, underneath everything the rest of this arc enforces. 3 mistakes recur here. First, picking a model because it's familiar rather than because it fits. Defaulting to RBAC for a genuinely relational, sharing-heavy domain because every past project used RBAC, then spending years bolting exceptions onto a role table that was never going to express the real permission structure. Second, the opposite error, adopting a full relationship graph system for a permission structure that's actually simple and stable, and paying the operational cost of running and consistency tuning a graph service for a problem 3 roles would have solved cleanly. Third, and most common in practice, treating the choice as permanent. An authorization model made sense for an organization at one size and one level of permission complexity, and nobody revisits it as the organization and the real-world relationships it needs to express grows past what that model was ever built to handle, which is exactly the multi-year gap that let Kestrel's original 3-role system quietly become a liability nobody had explicitly decided to accept. That closes Arc 3. We've gone from mesh-level mutual TLS as the enforcement layer to a centralized policy engine replacing logic scattered across services, to microsegmentation containing blast radius, to replacing the VPN for a distributed workforce, to securing the API layer against exactly the abuse a mesh and a policy engine can't see, to watching runtime behavior at the kernel when everything above it could be lying. And finally, this episode, to the authorization model underneath all 6 of those enforcement points, without which every one of them is just faithfully enforcing whatever answer that model hands it, right or wrong. Arc 4 asks a different question. Enforcement and the authorization model both assume there's a request to check in the first place. What happens to the data itself sitting on a disk once every access decision has already been made correctly? Next episode starts Arc 4, protecting data, with encryption at rest, KMS, envelope encryption, and the key hierarchies that decide who actually holds the keys to data. Every access control layer in this arc was built to protect. If you're building systems that need to survive being breached, not just avoid it, subscribe, and I'll see you in the next one.